Now we're looking at question 3, and it's electromagnetism. Mary, Martha and Luke are doing some experiments with wires and batteries. They connect a long wire to a car battery and a switch in the diagram below, and hold a wire, as shown on the diagram below. Then Luke closes the switch. They notice the wires move. We've got the charge on the electron given there. The diagram below shows the experiment looking down from above. First question. Referring to the second diagram, so I won't worry about the first diagram, determine the direction of the magnetic field at the point X. So maybe we should just write this down. We're looking for the magnetic field at the point X due to, due to the wire AB, so due to this side. So there's clearly a magnetic field produced at X by the wire CD, but we're interested in from AB what's produced for X. So if we use the right hand grip rule, we'll mark this in red, the right hand grip rule, we've got the current flow going around that way and back around here. So the current along AB is that way. With our right hand grip rule, my thumb is the direction of the conventional current and my fingers are going to grip the wire going up, so I'll represent it with dots on this side, and going down into the page on this side. So the direction of the magnetic field at X is on the same side as the dots coming out of the page, so we would choose out of the page for this one. The direction of the magnetic force on CD. Now this time we're taking into account both the magnetic field produced by AB and the magnetic field produced by CD, because it's current going through both of those. And then what's going to happen. So if we use our right hand rule, I better go for a different colour this time. For CD, we've got current flowing in that direction, so our thumb is going to point in that direction. That means we've got down into the page on the top part and coming up and out of the page on here. So our magnetic field is kind of pushing against each other, so we should see a movement towards the top of the page for the force. Well, it's not movement towards the top of the page, but the direction of the magnetic force on CD is pushing it away from AB, which is towards the top of the page. Okay, and you don't have to get into the reasons why, but basically, if the current was going in the same direction along DC as it is along AB, then the magnetic fields would combine. And the way they are, they're going in opposite directions. The current, that is, going in opposite directions. Therefore, the magnetic field, both coming out, is going to push away from each other. Okay, it's sort of like the like poles repelling thing. Moving on, B. The length of the wire between Mary and Martha is 5 meters. The size of the force between the wires is 0.013 newtons. That's 3 significant figures. We're still limited by the 2 significant figures of 5 meters. The current in the wire is 35 amps, also 2 significant figures. Calculate the size of the magnetic field at the point X and give the correct unit with your answer. Okay, so we should write down all of the things that we have, or just highlight them. So we've got a force, we've got a distance or a length. Okay, often with these electromagnetism ones you're using a length rather than a distance, so remember to write L. And we've got a current, I. And we're trying to find the magnetic field, strength, the size of the magnetic field. That looks nice because I can see a formula in the formula sheet that links all those. It's F equals B I L, and we can rearrange that for B and go B equals F over I L, and then we can plug all of those numbers in. I'm not going to go through that and do that for you, but you'll end up with 7.4 times 10 to the minus 5 Teslas. Remember, Teslas is the unit, so whatever your answer is, 7.4 times 10 to the minus 5 Teslas, or Tesla. A little bit unclear. Teslas would be plural, I imagine, but sometimes sheep is sheep for plural. Anyway, carrying on. Mary and Martha try to produce an electric current by spinning the wire in a circle like the skipping rope. So, like a skipping rope, so that it cuts across the Earth's magnetic field as shown on the diagram below. The ends of the wire connected to sensitive centre zero ammeter, which we can see just down there. And that's centre zero ammeter means that the little needle can move either side. So you'd imagine as it goes in one direction across the magnetic field, you're going to see the needle moving in one direction, then and as it goes the other way across the magnetic field, that is the wire cutting the magnetic field, the needle will go in the other direction. There may be a question related to that. We'll see. So the average speed of any part of the wire is 3 meters per second. So it seems like we're being set up for another mathematical question. That's a velocity. The wire's resistance is 1.5 ohms. The length of the wire remains at 5.0 meters. So that's a length. And we were given the Earth's magnetic field up the top there, B. Calculate the size of the maximum current in the wire. So we're after I. Okay, so usually with an Ohm's law type calculation, I equals V over R. We've got the resistance, but we don't have the voltage. However, looking around, remember we've got a little velocity there, it's not a voltage. We do know that from our formula lists and from doing it in class and knowing that there's a way to calculate all of this, V equals B, small v, or velocity with a wiggly underline for a vector, times the length will work, and that will give us the voltage induced across the wire. One problem or assumption to make is that 5 meters is the length curved. So I think we can safely assume, although it might be a good idea to write it, that we're assuming that the 5 meters is this length. So we're going to assume that. Otherwise we can't do the question that easily. And it's getting beyond level 2 physics. So let's just go ahead and set that up properly, or finish it setting it up. I guess we're going to do calculate the voltage this way, then we're going to calculate the current that way. I'm just going to combine the equations together. You can do all the tricky maths, all the simple maths, plugging those numbers in your own time, but the key thing that I'm trying to get across once again is the concept of how to do it. BVL over R. So you can see we've substituted the V part into the top of that equation over R. When you put it all together, I don't know what answer you get because my screen's just gone blank on my computer. But that's the process that you do for calculating it. Will be a very small current too. D. Mary and Martha have been told that more wire will produce a larger current. They try the arrangement shown in the diagram below, swinging both sides of the wire loop together. Explain what happens to the size of the maximum current. The size of the maximum current. Now, maximum current is produced when the wire cuts the field. I guess in the previous one we were calculating that average because we were given averages. This time we're dealing with the maximum. But the maximum is going to be when it cuts perfectly perpendicularly, which is when the wire would be kind of sideways, either going down on one side or coming up on the other, but cutting that field perfectly. But we don't even really have to worry about all those sorts of details, because if you look carefully at the diagram, the wire goes up that direction and then it comes back in the other direction before going down again. So across a single wire, here's my diagram here, we would have a voltage induced in one direction, but with the wire going back the other direction, we've got the same voltage induced in the opposite direction. Or in fact that's not correctly right. It's also inducing a voltage in that direction, but relative to the wire itself, both of those pieces of wire are going to be driving charges into that end of the wire. So the maximum current is going to be 0 because both of those voltages are pushing in the same direction relative to the girls, but in opposite directions relative to the wire and the flow of current in a circuit. Because they're pushing in opposite directions, you will get 0 current. And you need to explain all of those details to get your excellence. There you go.